In this example, we have a ladder sliding down the side of a wall, which of course would be a horrible experience if you're actually standing on the ladder. But let's see how this goes. It says the top of a ladder slides down a vertical wall at a rate of 0.15 meters per second. At the moment when the bottom of the ladder is 3 meters from the wall, it slides away from the wall at a rate of 0.2 meters per second. How long is the ladder? Okay, well, we have rates everywhere in this, so clearly this is going to be a related rates exercise. So let's bring up our steps for related rates. Okay, step 1, read and reread the problem to gain an intuitive understanding. Sketch a diagram if possible. Identify the rates that are given and the rate that is to be determined. Okay, so let's go back to the example and do all that. Okay, so we've read the problem. Let's set up a diagram so we can better understand what's happening here. Okay, so here's a ladder leaning against a wall, sliding down it, so this bottom part's coming out and this top part's going down. Let's call this distance down here x, and the height of the ladder on the wall y, and the length of the ladder we can call z. Right? I'm just putting in some information, right? Just filling in everything that we can. We also know some things. Let's call this velocity in the x direction dx dt perhaps. That gives us this velocity. And falling down, we'll do dy dt, right? So that's going down. Okay, so at least we have now a visual representation of what's happening. Let's more clearly list our givens and our goals here to be very specific about what we have and what we're looking for. So what's given? Well, we know that dy dt is always, that's falling down at a constant rate. So that's sliding down at what? 0.15. I'm actually going to make this negative. Since it's going down, we're going to define down and left as negative directions and up and to the right as positive directions. So we have negative 0.15. Let's clean this up. Negative 0.15 meters per second. We also know that dx dt, x dt is, well, it's changing, right? So when this thing first starts to fall, dx dt is going to be fairly slow as it slides out. And then as it goes down, 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 that dx dt is going to kick out faster and faster and faster. So it's not a constant. We have to say when this is happening. And we're interested when x is 3 meters. At that instant, dx dt is 0.2 meters per second. And our goal is to find the length of the ladder, z. Okay, so this is good progress. Let's go back to our steps and check in there. We are on to step 2. Write an equation that relates the various quantities of the exercise. If necessary, use geometry to eliminate a variable. Well, you're pretty much always going to need geometry somehow in step 2. So let's see how we can apply it in this example. Well, these are called related rate exercises for a reason, because we're relating all the rates together. So we need an equation that's going to relate x, y, and z, and dy dt, and dx dt possibly. Well, we can get those related if we can just relate x, y, and z. Then when we take the derivative, the rates will be related. So can you think of an equation that relates x, y, and z? Perhaps the Pythagorean theorem. So x squared plus y squared equals z squared. There we go. We have now related all the variables in the situation with one very effective equation. On to step 3. Step 3 says use the chain rule to differentiate both sides with respect to t. Okay, well, I'm always down for some chain rule. So we'll come in here, d by dt of both sides. Okay, d by dt. Alright, so doing this derivative gives us about 2x dx dt plus 2y dy dt equals 2z dz dt. Alright, so there's our calculus step. Let's check in with our steps to see what to do next. On to step 4, substitute known values and solve for the desired quantity. Okay, so now we're just plugging everything in. But before we do that, let's take a look at this. Note that we could factor a 2 out of both sides and just divide that out, right? Divide everything in here by 2, and that gets rid of all these 2's. Furthermore, what's dz dt? Is the ladder changing length at all in this process? No. It's sliding down the wall, but it's not getting any longer or shorter. So, incredibly, this whole term is 0. So now we can plug in what's left. Now we're interested at this moment where x equals 3 meters. So I'm going to plug in 3 for x. And then we decided at that moment dx dt is 0.2 plus, well then y, we don't know what y is, but we know what dy dt is. We decided that was negative 0.15 equals 0. Okay, well we can solve this for y. So y must be 3 times 0.2, 3 times 0.2, all divided by 0.15. Calculate that out, we get 4. Okay, so now we're making progress for sure. We have y equals 4. What does that mean? That means at this moment when x equals 3, so let's go back up to our diagram. At this instant in time when x happens to be 3 meters, y is 4 meters, and we want to know what z is. Well, now we're just back to good old Pythagorean theorem again, right? X squared plus y squared, so we have 3 squared plus 4 squared equals z squared. So z is going to be the positive square root because we're only interested in positive distances here of 9 plus 16. Well, how nice. Square root of 25 is indeed 5. 5 what? Let's throw on some units. Looks like we're dealing with meters for distance in this case. And there we have it. The last step is just to check to see if this is a reasonable answer. There it is, step 5. Check that the answer is reasonable. Well, yeah, it's reasonable, right? 5 meters. I would expect that to be about the scale of the ladder. Okay, we're not trying to really fine tune it, but if we got, 0.15 meters, I would say that's probably a little small. If we got 50 meters, I'd say, ooh, I think something might be wrong there. That's a little large. But 5 meters is about the scale that we're expecting when we're talking about distances like 3 meters from a wall. So it's reasonable. It's just a quick filter to make sure that our answer isn't completely outrageous.